This is the first recording for Math 150. I was having a little bit of trouble teaching to nobody, so my nephews gave me the courtesy of finding me an audience. They seem like they would be really good listeners, so they will be my students for today. Maybe they'll even participate, you never know. Okay, so we're going to pick up where we left off. If you remember, we left off with fractiles. So when we met the last week, we were talking about quartiles and box and whisker plots. So quartiles, if you remember, took our data sets and divided them into 4 equal parts. So we had a Q1, a Q2, and a Q3. And what we did is we took the median of the list, and that was Q2. Q1 was the median of the first half of the list. Q3 was the median of the second half of the list. Now, we'll be reviewing quartiles in the next video, because the next video will be a review of both what we do right now and what we did in class before classes ended. We're going to move on though. So we have quartiles, but then we also have something like deciles. So deciles, for example, divide the data into 10 equal parts. Essentially, we can divide the data into as many parts as we want, whatever we think is going to be useful. But actually, the most useful for us are just percentiles. So that's what we're going to start talking about today, are the percentiles. So percentiles divide the data into 100 equal parts. Think of it as we have 100%. So each set of data would be like 1%. Okay, so percentiles This does not mean that we're going to take every data set and literally divide it into 100 parts. We can do this in a much easier way. The purpose of the percentiles is it's like a point of comparison. It's ways that we can compare different data points. So, for example, we do this with your GPAs, right? We rank you. If any of you have taken the SATs, we do it with your SATs. And what we're looking for is where your GPA falls or your SAT scores falls with respect to other students, okay? So a data point that is under 5% is unusually low. And if it's over 95%, it's unusually high. So if you think about it as a class and you're in the bottom 5% of the class, then you would be in an unusually low ranking. And if you're in the top 5% of the class, then you're in an unusually high ranking. Okay. So we'll say anything below 5% is unusually low. And anything above 95% would be considered unusually high. But please note that this is open to interpretation, right? So some of you, most of you, including myself, would not just feel that anything above 95% is great, right? If we're in the top 90%, we may feel that's also really good. And we might feel, okay, well, I don't want to be in the bottom 5% of the class. That's too low. But if I'm in the bottom 50% of the class, that's okay. So we're kind of, we mix. These aren't very, very strict rules. But typically, if we're just talking about any data set, if you remember, we talked about outliers. These are equivalent to extreme outliers, okay? It's that, well, a little bit in between an outlier and an extreme outlier, okay? So again, it's open to interpretation as to whether something is good or bad, but unusually high or unusually low would be within 5 to 95%, outside of that. Okay, so think of it like this. If you have all of your data falling between these two numbers, and this is the 5% mark, and this is the 95% mark, then anything outside of here is unusually high or unusually low. Don't worry, in this class over here, everybody is within that 5 to 95% mark. So no worries, they're pretty great. Okay, so what does this mean for us? Okay, what this means is, suppose that you're in the 80th percentile. Okay, so if you're in the 80th percentile, what this means is that 80% of the data is at or below you. So it means, in this case, if you're talking about where you rank in a class, it means 80% of the students are at or below your score. So they're performing at or below your level. So if we take a look at this over here, if this is the 80th percentile, okay, so that's percent with an ILE, that's how I'm going to abbreviate percentiles sometimes. What this means is that 80% of the data falls here. It does not mean that you have an 80. It means 80% of the data is below you. So if we lined up everybody in the class here and we took the 80th percentile, we're saying 80% of the students in this class right here are at or below. Okay, so for example, if we took this nice little bear that we have in the corner here, if we took this nice little bear that we have in the corner here, if he's in the 80th percentile of the class, then we're saying 80% of the people here scored below him, and 20% scored above him. So if all of the tests ranged between 10 and 25, okay, he would be at the 80th percentile score. So notice that does not mean 80%. It doesn't mean his score is 80. It means 80% if his score is, let's say, 20. 80% of the people scored a 20 or below, and 20% of the people scored a 20 or above. That's what we're saying. Okay, so let's start thinking about how we would calculate these percentiles. So we don't have to, as I said, we don't want to divide our data set into 100 pieces because sometimes there's less than 100 pieces of data. So in order to find the percentile that a piece of data is in, we can actually set up the really, really simple formula. Okay, so to find that percentile, we would say the percentile of X. So remember, X represents any piece of data. And what we do is we say this is the number of pieces of data less than X. Over the total number of pieces of data. And because it's a percentile, we're going to multiply by 100. So the multiplication by 100 is what tells us that we're talking about a percentile versus a quartile or something else. So if you remember from earlier in the semester, the total number of pieces of data is always referred to as n. And what we want to do also is we always want to take this and round to the nearest whole number. So typically we wouldn't want to say that we're in the 82.3 percentile. It just doesn't make sense. Okay, so let's take an example of a set of data. So I'm just going to write out some numbers here. There are 25 numbers that are in the list. So we have 16, 18, 18, 23, 25, 27, 30, 33, 34, 34, 35, 35, 36, 40, 40, 41, 44, 45, 47, 49, 50, 51, 51, 52, and 52. Okay. And we want to find out what percentile the number 34 is in. Okay, and this data, we're going to say that it represents tuition costs at 25 schools around the country in thousands of dollars. So for example, the most expensive school right now in this particular list is $52,000 per year, and the least expensive school is $16,000 per year. So we want to know, well, what percentile does 34 wind up in? So simple to do, we're just going to figure out how many pieces of data are below 34. So notice there are two 34s here. We're not going to count these. We want everything that's less than 34. So if we count the number of pieces of data less than 34, we have 16, 18, 23, 25, 27, 30, and 33. You can see that I can highlight in a very, very straight line here. And if we count that, we can see that there are 8 pieces of data here. So let's calculate the percentile. So there are 8 pieces of data that are less than 34. And I told you already that n is equal to 25. So there are 25 schools that we looked at. So n is equal to 25. Okay. So if we want to calculate the percentile, all we have to do is say 8 That's not a very nice 8. This is very new, writing on this type of board. So 8 over 25 times 100. And if we find 8 over 25 times 100, let's bring up our calculator. And this actually turns out to be exactly 32%. So we don't even have to round, okay? Exactly 32%. Okay, meaning 34 is in the 32nd percentile. 32% of the data is less than 34, which if we do the math, that means 68%, whatever is left over, 68% is greater than or equal to 34. Okay, so let's do the same for another data point. Let's say that we want to find the percentile. (41) is in. So we're going to do the same thing. We're going to highlight anything that is less than 41. So we have the 16, we have the 18, 23, 25, 27, 30, 33, 34, 34, 35, 35, 36, 40, and 40. So again, we don't include the 41, okay? It's everything that's less than 41. So we have the 8s, then we have 9, 10, 11, 12, 13, 14, 15. So there are 15 data points that are less than 41. So we would write, and I keep saying pieces of data. If you remember from, I think I said this on the very first day of class, one piece of data is called a datum. So 15 pieces of data are less than 41. So if we do 15 over 25, times 100. If we bring this up on our calculator, if we have 15 divided by 25, you'll see we get 0.6, and when we multiply by 100, this gives us exactly 60%. So 41 is in the 60th percentile. Meaning 60% of the data is less than 41. Let's do one more. Let's say, for example, that we wanted to know what percentile 52 was in. And we might change the way in which we word this question. We would say, in what percentile is 52? So if we go back and we look at our data here, we can see all of these numbers are less than 52. That's 23 numbers. So we can count that, or we know that there are 25 and 2 of them are 52. So there are 23 less than 52. So 23 numbers less than 52. Remember that this means less than. So we're going to say that the percentile is 23 over 25. We're going to multiply by 100. So notice this bottom number is always the same. That's because it's the total number of pieces of data. And again, if we bring up our calculator, 23 divided by 25 is 0.92. And then when we multiply by 100, we get 92%. So 52 is in the 92nd percentile. And notice in this case, there's nothing that's unusually high or unusually low, okay? And that's more likely to happen when you have a smaller data set, because when there are only 25 pieces of data, you don't always have a 95th percentile. Your 95th percentile would be that very last number, and the 5th percentile would be that very, very first number. If we only had 5 pieces of data, for example, if we only took the first 5 pieces, so if we were only looking at a list that consisted of 16, 18, 18, 23, and 25, if we wanted to know the percentile of 25, that would be the 100th percentile. But if we wanted to know the percentile of, let's say, 18, that would be the 20th percentile, just right there. So there's not really an unusually high or an unusually low when we have such a small data set. Okay, so that's percentiles. And again, we use that really as a way to compare different pieces of data. So we'll know, okay, well, 52 is in the 92nd percentile, but 15 is in the 60th percentile. It gives us a little bit more of a comparison of the data. And it tells us, again, this also kind of tells us the spread of the data, because if we have 52 in the 92nd percentile, and then in the 60th percentile was 47, then that also tells us that the data is very close together, at least at the top. So it still gives us an idea of the spread. If you notice a lot of the things that we've done, including quartiles, that gives us an indication of the spread of the data, and we're able to see that through those box and whisker plots, which we will be looking at in the next video. the one thing I want to note, and I want to make sure that everybody remembers, is that your data has to be in order when you find percentiles. So it has no meaning unless you put it in order. This is probably intuitive since the numerator here is the number of numbers that are less than 52. And if this data had not been in order, then we wouldn't have even been able to calculate that. Okay, we wouldn't have been able to count the way that we did. Okay, when we did quartiles, we also did that in order. Okay, so the next thing that we look at is something called a standard score. So this is another point of comparison between different pieces of data. So what this does is it goes backwards. So here, we're given the mean, and I'm going to use the symbols for population, but this would be true for sample as well. So given the mean and standard deviation, we can determine the position of a piece of data. In the data set. Okay, this has two, we can describe it in two ways. It's the standard score or the z-score. What we're doing is, instead of finding a percentile, we're finding how many standard deviations away from the mean we are. So the number of standard deviations away from the mean. And I'll remind you that one of the ways that we described an outlier is we said if it's more than 1.5 standard deviations away from the mean. So if we start at the mean and we go 1.5 standard deviations below it, anything past that would be an outlier. If we go 1.5 standard deviations above that, anything past it would be an outlier. So this kind of, again, it goes backwards. We're trying to figure out, instead of what our outliers are, we're trying to figure out, is something an outlier? And if it's not, then let's be even more specific. How many standard deviations away from the mean? So first of all, our z-score, this is also a formula that we can use, but the formula makes sense, okay? So we call it a z-score, so it's z equals, and then it's the value, so the piece of data, minus the mean over the standard deviation. Okay, this is the piece of data, which remember, again, we refer to this as x minus the mean over the standard deviation. Okay, here's what this is doing. It's saying, okay, let's say that this is the mean. And let's say that this is x, okay? It's looking for this distance here. It's looking for this distance in the middle. So we take this distance in the middle, and then what we're going to do is we're going to break this up into pieces, and those pieces are going to be lengths that are equal to the standard deviation. So we're going to divide this into, let's say that the standard deviation were 3, we would divide this into lengths that are equal to the standard deviation. So this would be 1 standard deviation. This would be 2 standard deviations. And then this might be 3 standard deviations. So that would mean x is 3 standard deviations from the mean. Okay, let's change this though. Let's look at another case just so that you can make sure that you know how it works. So this time, let's say that this is our mean again. And we'll say that this is our data value. Okay, and again, we're going to measure our distance in between. So here's the distance in between. And here our standard deviation might be different. Let's say our standard deviation is this length. So this is the length of a standard deviation. Well, what this is doing is it's telling us that, okay, this is actually, here's a second standard deviation from the mean. So x is now not 3 standard deviations, but it's between 1 and 2 standard deviations from the mean. So this is 1 standard deviation from the mean. This would be a second standard deviation from the mean. So when we take this distance here and we divide by the standard deviation, what we're saying is how many standard deviations fit into this little place. And we'll see that it's 1 and it looks like about 1.5 here. Okay, so here we would be saying x is 1.5 standard deviations from the mean. Okay, so let's do this with some real data. Now, before we do that, we should know that if z is less than 0, because it can be negative, what that means is that the value minus the mean is going to give us a negative number. Now, the way that happens is if the value is less than the mean, okay? So if z is less than 0, if it's negative, that's okay. All it means is that x is below the mean. And if z is greater than 0, meaning it's positive, then it's just telling us that x is above the mean. And we already discussed that if Z is greater than 1.5, meaning we're more than 1.5 standard deviations away from the mean, okay, so this would be saying that we're 1.5 standard deviations above the mean, or we're 1.5 standard deviations below the mean, meaning Z is less than negative 1.5. Then we're saying that X is an outlier. Okay. So let's say that we're discussing the speed of a vehicle. So suppose that the mean speed of a vehicle is 56 miles per hour. On the highway. With a standard deviation of 4 miles per hour. And I'm going to change this to vehicles so that it's clearer. So if we take the speed of all of the vehicles on the highway, the mean is 56 miles per hour and the standard deviation is 4 miles per hour. So we're going to determine the z-score for 3 different cars. So we're going to find the z-score for a car going 62 miles per hour, 47 miles per hour, and 56 miles per hour. Now, one of the reasons that we might use this is to try and determine, I'm sorry, I don't know why this is here. One of the things that we would be doing, one of the purposes of this might be to determine, are we driving safely on the highway? We don't want to drive too fast and we don't want to drive too slow. So let's see what's going on here. Okay, so let's start with the 62 miles per hour. So we're going to say X is equal to 62. So when X is equal to 62, the z-score, we're going to take 62. We're going to subtract the 56 we get from the mean. So we're using this 56 here, and then divide it by 4. And if we go to our calculator, we can see 62 minus 56 divided by 4 is 1.5. So we're 1.5 standard deviations. And in this case, we're above the mean. Because it's positive. And it makes sense. 62 is greater than 56. Okay. We're going to repeat this. for the data point of 47. So our z-score is 47 minus 56. And again, we divide by 4. We're trying to figure out how many of those standard deviations we're getting into this distance between 47 and 56. So again, we can go and calculate this. 47 minus 56. Notice our answer is negative. So our answer is negative because 47 is below the mean. And then we divide by 4 and we get to negative 2.25. So 2.25 standard deviations. I'm just going to abbreviate that, below the mean. And finally, if we do it for 56, our z-score is 56 minus 56 over 4. This is just 0. So what this tells you is this is the mean. Okay. And unusually high or unusually low in this case would be outside the 2 standard deviations. So we talk about skew left and skew right. If we assume the data is symmetrical, okay, 95% of the data falls within 2 standard deviations of the mean. And we will talk about this a lot more. And in fact, .7% falls within 3 standard deviations. So you can see why we would call something that's outside of 3 standard deviations an extreme outlier. Okay, again, if this is our mean, and this is 1 standard deviation, this is 2 standard deviations, and this is 3 standard deviations. And then if we go on this side, if this is 1 standard deviation, then we go 2 standard deviations, and then we go a 3rd standard deviation. Okay. I'm going to pause this for a minute. Okay, so if we record this as 1 standard deviation, 2 standard deviations, and 3 standard deviations, from the mean, Then over here, %95 of the data falls between here. Okay, and within the 3 standard deviations, this will include 99.7%. So only 0.3% will fall out here or out here. Okay, again, this assumes that the data is symmetrical. So one of the other things that we can do is we can look and see, we can compare different pieces of data to look at other things. So for example, suppose the mean monthly utility bill is $70 and the standard deviation is $8. Let's find the z-score for $60. So the z-score would be 60 minus 72 over 8. And if we figure this out, you're going to see that 60 minus 72 is -12, so we're below the mean, so that makes sense. And then here we divide by 8, and we see that we're 1.5 standard deviations below the mean. And this might tell us, oh, maybe it has to do with how much electricity we used, or maybe our particular utility company is better and they're undercharging us. So this could be helpful there, or it might help us monitor our electricity use. So for example, let's say that instead we chose $92. This would be 92 minus 72 over 8. So notice we're using that standard deviation and that mean. 92 minus 72 gives us 20. We divide by 8, and this is 2.5 standard deviations above the mean. And this might tell us we are using too much electricity. Okay. And a lot of times we're looking for reasons that this is happening. It might be that this is a utility bill during the summer. Just want to make this a little bit darker. This is very unclear. I'm going to rewrite that. right? So we're using way too much electricity, or maybe it's a month during the summer. Because then if you pay for your own electricity, you're using your air conditioning, and that's going to cost you more. Okay. And then the final reason that we might use a z-score is to compare different data. So they could be different data sets entirely. We might do this if we're looking at arrest records in different states. If we look at, let's say, even the coronavirus, we might do comparisons in the number of people who tested positive from one state to the next, or from one country to the next. We might do it even in terms of the number of deaths, or the number of deaths that result from the coronavirus versus the number of deaths that are a result of hospitals being overcrowded. So it's a way for us to take different data sets and compare and say, okay, well, one thing is true for one data set, but not true for another data set. So let's take an example. What we're going to use is heights. So we're going to look at the heights of men and women. So for men, this is true information. The average height is 69.9 inches. And the standard deviation, and notice we're using S because it's a sample, is 3 inches. Whereas for women, the average height is 64.3 inches, and the standard deviation is 2.6 inches. So we're going to look at the z-score. For a person who is 6 feet tall. So notice that our mean and standard deviation are in inches, so we're going to convert this to inches. So 6 feet is equal to 72 inches. Okay, so we're going to calculate the z-score if we're a man versus a woman. So 16, the z-score, this is if we're talking about a man. We have 72 minus 69.9 over 3. Notice that for men, the heights, there's a much bigger, not much bigger, slightly bigger spread in heights. The standard deviation is 3, whereas for women, the spread in heights is a little bit less. So if we calculate this, 72 minus 69.9, and we divide by 3, and we're only 0.7 standard deviations away from the mean. Now we're going to do the same thing for a woman. We're going to calculate the number of standard deviations away from the mean we are. If this person were a woman. So this time, instead of 69.9, we're using 64.3. And instead of dividing by 3, we're going to divide by 2.6. And notice here, this is 3. This is 3 standard deviations from the mean. So big difference. This is very tall for a woman. Okay, it's unusual. Whereas this, it's not so tall for a man. And I wouldn't say it's common, but I would say it's not uncommon. Okay. Now, let's take a look at this z-score for someone who's 5 feet tall. And I'm sure that you're all already making your predictions. So 5 feet is equivalent to 60 inches. So let's first do our calculations for a man. So here, our z-score, we're going to do 60 minus 69.9 over 3. And this is negative 3.3. So notice this is very short for a man. It's unusual. It's outside that 3 standard deviation range. Okay, very short. Now we can do the same thing for a woman. And again, I'm sure that you can all kind of predict what's going to happen here. So we do 60 minus 64.3. And we divide by 2.6. And this one, it's only 1.65. So notice we're rounding to the nearest hundredth. This is a 3 over here, so we round down. So it's 1.65 below the mean. So this is short for a woman. But again, I wouldn't say that it's common, but it's not uncommon. You will see women who are 5 feet. Now, what this tells you is that you will see more men who are 6 feet tall than you will see women who are 5 feet tall. Okay, so we can do a comparison between heights, and you can see that these are completely different data sets, but it does give us some idea as to comparing. Okay, in general, women are shorter than men. Okay, so that is it for this lecture. So we went over percentiles and we went over z-scores. I will post a quiz on Thursday. So the quiz on Thursday is going to be essentially what would have been your quiz this week. It will cover quartiles, box and whisker plots, percentiles, and z-scores. And that will be it. I will have another lecture posted probably sometime this weekend that just reviews the box and whisker plots for you, because I know that that was a while ago. And I will also post a review sheet again, probably within the next few days. That'll just prepare you for the quiz. Now, I will post another lecture before Monday, most likely, or maybe not before Monday, but another lecture at the beginning of the week, which will cover new material that will not be on the quiz. So the only material on the quiz are your quartiles and box and whisker plots and what we covered in this lecture. That's it. Anything else is new material, and that'll be covered in a future quiz. And that is it for this lecture. Thank you very much.